Alright, silly people, here's the situation. We have a, basically a wire um, that is infinitesimally thin and infinitely long, and it happens to be moving um, in the z direction uh, with a speed v, and we happen to know that in its own rest frame that the charge density, the linear charge density anyway, um, is just given by Q naught. And we're meant to find the electric field, magnetic fields, um, the charge density, and the current density um, in the rest frame and in the lab frame outside of the thing moving. So, in its own frame, it just takes the same form as like any other line charge field. It's 2 lambda prime r hat over r. So for us, that's like 2 q naught r hat over r. And since in its own rest frame there aren't any moving charges, so there's no current density, so there's no magnetic field. So the B is 0 in its own rest frame as well. Um, and then to get into the lab frame, I have here the equations for a Lorentz boost of the magnetic fields and electric fields, which I'm just going to copy down. This is beta dot E here, and then got B prime is just gamma B minus beta cross E minus gamma squared over gamma plus 1 beta vector beta dot B. Now we're looking for B and E, not E prime and B prime. So we're going to have to invert these equations. Um, and to do that, all you really have to do is change the sign on the dot product terms in either one. So instead of having plus beta cross B, you're going to have minus beta cross B in there. But then everything else will follow suit, and this will be a B prime actually. Gamma plus 1, and this is going to be beta dot E prime. And then for B, you'll have um, gamma B prime minus beta, or actually plus now, cross E prime minus gamma squared over gamma plus 1 beta times uh, beta dot B prime. Right. So that's cool. We can now just use these equations to figure out what these are. The electric field will be given by gamma, and then E prime was just 2q naught r hat over r. Um, and then, but B prime was 0, remember? So that's done. And then continuing, we'll need a beta dot E, so it's minus gamma squared over gamma plus 1, and beta, the vector, is in the z direction, so it's just the magnitude of beta times z hat, and then you have beta z hat dot r hat for, or actually, E prime is 2q naught over r times r hat. But z hat dot r hat is 0 because they're orthogonal unit vectors. So we just get this r hat over r, 2 gamma q naught. Okay. Similarly, we can go ahead and get the B field then. Since we have B prime, this is 0. But then we'll still have a term which is the beta vector, which is in the z direction, crossed with the electric field, which is 2q naught over r hat. So we got that to work with, but then this term is 0 again, because now b prime is 0, so the whole thing goes to 0. Okay. Then we have gamma beta 2q naught over r, and then z hat cross r hat is just phi hat. This is cylindrical coordinates. So yeah. So that's looking fine. And I'm gonna even just leave the fields like that and move on to calculating the current densities. So in its own rest frame, we already kind of said this, but there's no current density in the wire's own rest frame because it's a statics problem in its own rest frame, so it's 0. But the charge density is not 0. We'll just have to convert it from being a linear charge density into being a volume charge density, which you can just do by dividing by 2 pi r the circumference of the cylinder and multiplying with the Dirac delta. So we get q naught over 2 pi r, and then the Dirac delta r. Now, the current density is a 4 vector. Specifically, it has the terms which correspond to rho prime. The charge density is the first index, and then the other indices are just the indices of the 3 vector current density, but all these are 0, so in the prime frame anyway. And since it's a 4 vector, we can Lorentz transform it like a 4 vector. So it will look like this. The 0th component in the prime frame will be gamma times the 0th component in the lab frame minus beta times jz, and it's jz specifically because the rod is moving in the z direction with the speed v, so you only care about the z component of the 3 current density. And then similarly here, you get the jz minus beta j0, which is just given by rho minus beta jz equals just rho prime. So this equation we'll come back to. We'll work with this one first because the left-hand side is 0. We already kind of figured that out. So we have this stuff, and then J0 there, we'll have it turn into rho, and then we'll solve for Jz, so we get Jz is equal to just beta rho. And we'll shove that into this equation here and say that gamma rho minus beta squared rho is equal to rho prime. And then solve for rho, so we get gamma prime over, or rho prime over gamma times, and then divided by 1 minus beta squared. And you'll get back your rho, but then 1 minus beta squared is just the inverse of gamma squared. So you get gamma squared up here is rho. So you just get rho prime gamma is equal to rho. So we know what rho prime is. So we know that the charge density in the lab frame is just 2, or actually not 2, but q naught gamma over 2 pi r times the delta function, delta r. And that'll do. The charge density, we'll go back and we'll grab the um, z component of the current density and say that it will be just beta times q naught times gamma over 2 pi r delta r. That's all. Um, okay, now we need to then recalculate what the electric fields and B fields are in the laboratory frame. We need to calculate the electric fields and the magnetic fields in the laboratory frame. And to do that, I said that the electric field will now just be calculated by doing the same thing as before. So you take 2 times the linear charge density, divide by r, multiply by r hat. That's how you do line charge densities. It's just that the line charge density in the laboratory frame is now just equal to q naught gamma. So we have that this is 2 gamma q naught over r hat, which does match what we got before for the electric field, and you can do a similar thing for a magnetic field through Ampere's law or what have you, and then you get the same thing that you get for the first part, which was the magnetic field in the lab frame. And that should be good. So there you go.